Natural convection flow is simulated in 2D over a range of Rayleigh numbers and conditions. In these types of flows, fluid motion is driven solely by buoyancy forces resulting from temperature gradients within the fluid. Warm air, being lighter than cold air, rises upwards against gravity. We induce these flows by creating a hot plate boundary on one side and a cold plate boundary on the other side. Gravity then causes the fluid to mix and exchange energy within the space between the plates. We simulate the fluid within a linear domain between two flat plates and also a circular domain where the fluid is confined between two concentric boundaries. Within this circular domain, the force of gravity points inwards. Natural convection flows, where fluid motion is driven by heat, are extremely common in nature and can be demonstrated through numerous examples. These examples can include mixing and boiling, as shown here. If you look closely, you can observe the existence of cells within the flow, which is a common feature found in many convective flow situations. Weather patterns and cloud formation are also highly influenced by natural convection. The airflow patterns develop because the ground is warmed by the sun and the upper atmosphere is cool. This causes the air to rise in some areas and fall in others, thus creating many of the weather patterns we are all familiar with. In an extreme example, convective cells can be observed forming across the entire surface of the Sun, as shown in this close-up view from the Daniel K. Inouye Solar Telescope. The complex structure of the convective cells is clearly visible within this video. However, in this extreme situation, the size of each cell is approximately equivalent to the size of the entire state of Texas. In this first experiment, we show a simulation of natural convection within a circular domain at a Rayleigh number of 5 million. As stated earlier, the inner circle is hot, which drives the flow outward towards the cold outer boundary. In this animation, the colors represent the temperature of the fluid, with yellows and reds representing higher temperatures and blues and violets representing lower temperatures. We can also highlight the fluid's velocity vectors here to see a more detailed picture of the fluid motion. Small vortices and complex flow patterns can be seen throughout. Here, we also show the 2D unstructured and adaptive mesh used in the simulation. As can be seen here, the structure of the mesh follows the features of the flow, and it's this adaptive nature that ensures high accuracy of the computed solution throughout. Finally, we can add tracer particles to the flow in order to highlight the fluid motion even further. The Rayleigh number is quite high in this simulation, but what is shown here is a new simulation at a lower Rayleigh number of 250,000. As can be seen, the flow features are much more diffuse and less complex compared to the previous simulation. Here we present the simulation results for a range of Rayleigh numbers, ranging from 1,500 to 5 million. As can be seen, the flow patterns tend to become less complex and more diffuse as the Rayleigh numbers decrease. The lowest Rayleigh number, 1,500, falls below the critical value, resulting in no motion at all within the fluid for this condition. The subsequent Rayleigh number, 5,000, slightly surpasses the critical value, causing fluid motion. However, the flow patterns themselves remain constant and steady over time. The following simulation, conducted at a Rayleigh number of 80,000, slightly exceeds the threshold where the flow patterns become unstable over time, leading to the emergence of subtle motions. Significant fluid motion and complex flow patterns can be observed in all other simulations at higher Rayleigh numbers. In this next experiment, we are simulating natural convection within a linear domain with hot and cold plates on either side. As we expect, the temperature difference between the plates causes the fluid to rise against gravity and mix together. Similarly to the circular domain experiment, the Rayleigh number in this case is also 5 million, resulting in a very complex flow with many intricate details throughout. Despite being different from the results of the circular domain experiment, the overall flow features here are still very similar. We have simulated the same 6 Rayleigh number conditions as before. and you can see the results of those simulations here. Once again, although they are different, the flow features are still very similar overall to the results from the circular domain for each of the Rayleigh numbers. Here we show results from the two domain types together at a Rayleigh number of 1 million so that they can be compared with each other in more detail. All of these simulations and visualizations were carried out interactively within a web browser using the Digital Dynamics Studio from Digital Rocket Science.